class.
That's amazing. That's totally amazing.
Where is everyone? No one else is here.
There's 25 participants, but they're just hiding. They're trolling. Okay.
No, I mean no one is in the class. I'm in this classroom by myself.
Well, Michael, I think you're a little off-putting. You know, people just didn't want to hang out with you.
Yeah.
All right, everyone.
Jonathan's own
Hey, Nathan.
Jonathan's upside down.
Nice, Raph. I like the Stephen Hawking. That looks pretty good. Okay, guys. We should get to this. Otherwise, you guys are going to get bored, and I'm going to get thirsty. Okay. And once I start drinking, this whole show is over. So we've got some homework to do. Actually, that's when the show begins. All right. So we've got some work to do. We've got a pretty intense homework ahead of us. The Chapter 14 homework's no joke. Are we ready to get going on that?
Yeah. What page are we looking at?
Yeah.
We're looking at the problems in Chapter 14. Let me grab my book. Hold on.
I'm going to keep my background like
Jonathan.
this.
Yes.
All right, I'm going to get rid of this silly background so that we can actually do some work here.
Never mind. It's 488, 489, somewhere around there.
49?
488, 489.
All right. I got some problems. Riker, have you got a book too?
I got my book.
It kind of helps if you guys read because then I can take down the givens. Look, the first two problems are word problems, and they're a little bit nuts. So let's just kind of get into it. Riker, what's the first number?
I do not know.
Oh, hold on. If anyone knows, shout it out. Otherwise, I'm going to have to look it up.
Hold on. I'm pulling up the syllabus now in the schedule.
Which homework is this? Is this homework number 6, I think?
I think it's homework 6. I think.
I believe so. Could be wrong.
If it's homework 6, then the first one is Chapter 15, number 45.
Thank you, Hope. Homework number 6. Wait, no. Chapter 14, right?
Yeah,
Chapter 14.
but number 47.
This is homework number 6. Chapter 14,
Oh,
number 47.
Yeah, you're right. It's number 47. Sorry, I was looking at
47 is first.
Yeah.
That's fine. I'm going to go to speaker view so that you guys can see my board better, or I can see the recording can see the board better, rather.
So it's number 47, a really strong force. How would the interior temperature of the sun be different if the strong force that binds nuclei together were 10 times as strong?
Okay. And they want to know how will the interior
temperature be different?
All right. I think this is one among the hardest questions we will do all semester. So it's a word question. It involves writing a paragraph or so. But I'm going to have to share screen to kind of show you guys what's going on here. As a sort of explanation of how this works, I want to go to my lecture on the sun. Can you guys see what we're doing here?
Yes.
All right. And I want to talk to you guys a little bit about the interior fusion of the sun. The sun's interior temperature, hold on a sec. Function F5. Hold on. For some reason, my slideshow, it just doesn't want to function F5. All right, there we go. I don't know what that was all about. Let me scroll ahead here. And I want you guys to look for a minute at the layers of the sun. Now, the sun does not have a single uniform temperature. It's close to 6,000 Kelvin at the surface, the so-called photosphere. And as you burrow your way from the exterior of the sun down into the interior, the temperature rises quite dramatically. So the photosphere is 5,800 Kelvin. It gets up to, maybe 100,000 Kelvin in the convection zone. In the radiation zone, it goes up to maybe millions of Kelvin, up to maybe 10 million Kelvin. But once you hit this central core of the sun, which is maybe like the inner 15% of the sun's radius, this is where the star gets hot enough for fusion to occur. And the sun's central temperature today is a key value of 15 million Kelvin. Let's write that down. So the interior temperature of the sun is 15 million Kelvin. And this is important because that's the temperature at which hydrogen can fuse inside the center of the star. So this is the hydrogen fusion temperature in general. Actually, I think the hydrogen fusion temperature is just a teensy bit lower than this. But basically, by the time you get up to 15 million Kelvin, that's when hydrogen atoms can fuse. But I need you guys to think about what that would look like if you could travel into the interior of the sun and watch a bunch of atoms smash around together. Let's go back to share screen for a second here. Let's borrow our way down into the core and follow my slideshow. By the way, inside the core of the sun, you would discover that temperatures were so high that you were effectively just dealing with a completely ionized gas, a completely ionized plasma. And so this little cartoon was maybe one of the best cartoons that I could find to help you guys visualize it. Notice that you guys remember the composition of a hydrogen atom, right? What's the composition of a hydrogen atom? Somebody?
One proton, one electron.
Thank you. One proton and one electron. If you guys don't know that, you're probably screwed for the rest of this discussion, okay? Well, a hydrogen atom is one proton and one electron, okay? Notice that at 15 million Kelvin, hello, Liberty, at 15 million Kelvin, the electrons have been completely stripped off of the hydrogen atoms, and now the hydrogen has been dissociated into protons and electrons. And all these protons and electrons are bopping around together. But the protons and the electrons bopping around together, they're not strictly bouncing around like an ideal gas. And that's because in a perfectly ideal gas, the particles just kind of travel in straight lines until they smash into each other, just like pool balls on a pool table, or like basically, you know, BBs bouncing around inside of a box. This is what a gas of neutral atoms does. But think about how that might be different if instead of neutral atoms, you had a bunch of ionized protons and electrons. These things are going to be swimming around each other in a sort of complex bee dance where, slide 49, where the protons and the electrons have magnetic fields which interact with each other. And you guys remember how this works, right? Electrons repel other electrons, protons repel other protons, and electrons and protons are attracted to each other. But the temperature is much too high for these particles to interact. Now, what's happening here is to kick off our fusion, a proton is going to start off on a collision course with another proton, but instead of just smashing into each other, they're going to do something similar to, hold on a second. Something similar to what would happen if you took two magnets and tried to thrust two north poles against each other. If I take these two magnets and I try to press their two north poles together, I start to feel that magnetic pressure, that magnetic field interaction, and the two magnets, they kind of, they slide off to the side. Now, if I try really hard, I might be strong enough to compress these things together, but it's hard to do it. You see how they want to just kind of slide off each other? And the two magnets just want to go, they want to deflect one another. So a similar thing is happening here with these two protons, except it's their electric fields that are causing each other to repel. They're on a collision course, but the electric fields are going to cause the particles to deflect. And when they deflect, that avoids the collision.
You want us to draw this illustration?
I don't think it's a bad idea. Yes, it will increase the length of your problem answer, but I don't see how we're going to answer this question. I mean, I can just tell you what the answer is in 15 seconds, but I'm assuming, maybe naively, that we want to learn and understand it. And drawing this picture is part of the understanding, in my opinion. So okay. I promise some of the other questions aren't as long-winded, but this is a long-winded question. There's just no way around it. The two particles that are going to interact, the two protons, they're gonna have a minimum distance of interaction. In nuclear physics, they call this the impact parameter. And the impact parameter tells us how close the two protons get before they deflect and fling away from each other. Let's imagine what happens inside the star as the temperature of the particles gets higher and higher. You guys know that the temperature is kind of like the speeds of the particles. So as the temperature of the interior of a star increases, the kinetic energies and the speeds of the particles increase, and they get closer and closer together until they fling apart. So in the outer layers of the star where the temperature is colder, the particles can only get so close before they kind of just fling apart. But as the speeds of the two particles gets faster and faster and faster, you're pressing them closer and closer together before they fling off from one another. At 15 million Kelvin, something special happens. The impact parameter gets so close that the particles can almost touch. And when the two protons get within a certain minimum distance from each other, a new force of nature takes over called the strong nuclear force. And this strong nuclear force is capable of gluing the two protons together, but only over very, very short distances, comparable to the radius of a proton. So nuclear forces are only strong, they only work when the distances are about the size of an atomic nucleus or so. You might think of a nuclear force in some ways as being kind of like Velcro. Velcro can stick two particles together, but only if they get close enough for the little Velcro fuzz to touch each other. In order for these nuclear reactions to take place, you have to transmute one of the protons into a neutron. And I'll be explaining that in our next class. In any case, once the two particles glue together, then the nuclear fusion starts up, and that's when you can produce gamma rays which heat up the star. So I want you guys to look at the process of the proton-proton chain. I'm going to go back. Are you guys seeing my screen here?
Yep.
Yeah.
Yep.
So in the proton-proton chain, this is a little bit of a techie kind of diagram here, but follow along with me. In the first step, two hydrogens slam together, and that's basically just two protons, and they emit some antiparticles and some neutrinos. But first, one of the protons turns into a neutron, and it becomes a deuterium nucleus. And then the deuterium nucleus slams violently into another hydrogen, and this is an important step. This is where energy is released in the form of a short wavelength high energy gamma ray, and then you glue yourself into a helium-3 nucleus, and then two helium-3 nuclei slam together to make a proper helium-4 nucleus. And the net reaction, which I'll have to skip ahead for, is that four hydrogens are going to come together and make one helium atom and release some energy, okay? Now, this second stage of the proton-proton chain, this is where the photons in the form of gamma rays are produced. And these actually, you know what? I've got a much better picture of this. This picture is not helpful for you guys, but if you'll bear with me, I realize that I have a slightly better view of the proton-proton chain. That's a little more cartoony, but just a little nicer on the eyes as an information graphic. Pardon me for 1 second here. I need to eventually update the slides. This is probably one of the cleanest graphics depicting the proton-proton chain that I've ever seen. So here you have your two protons. They slam together to make a deuteron, which is the nucleus of deuterium. The deuteron then slams into another proton, and here's where you form the energy of the sun. You form a gamma ray, and then two helium-3 nuclei slam together to make, to make a helium-4 nucleus. But here's the important part. This is the net reaction shown over here in the pink box. In the pink box, you can see that four protons slam together and create a helium nucleus, and they emit energy in the form of two gamma rays. Now, those gamma rays are going to go out into the interior of the sun. They are going to heat up the sun, and they are going to maintain hydrostatic equilibrium. Great. let's try to get back to the question and see where we're at.
Real quick. So when the two protons hit each other, and the strong nuclear fusion force thing happens, does it switch to a neutron? Like, how does that?
Oh yeah, that's some really nutty shit goes on there. Hey, I want to just blow your mind for a second here, Nathan.
You're already
know
doing
that
it.
A neutron is actually a proton and an electron squeezed together. In free space, if you fling a neutron out of an atomic nucleus, a neutron will disintegrate in about 15 seconds or so, and it will destroy itself, and it will decompose into a proton, an electron, and a tiny particle called a neutrino. So if you leave a neutron alone outside of an atomic nucleus, it basically just deconstructs itself into its component particles.
That
Now-
actually makes a lot of sense, because the graph that you were showing had a little white dot, and I was like, what is that? But that's the electron that's merging with it.
Dude, honestly, we were going to have a long discussion about nuclear physics. It's kind of crazy. Believe it or not, the sun actually takes two gamma rays, and the two gamma rays collide together and create a particle-antiparticle pair of an electron and a positron. You know what? Let's just save that for next time. If you get me excited to talk about particle-antiparticle collisions, I am going to go on a rant, and then we're going to have the same problem we had during lecture today.
We're going to be here all day.
All right, yeah. So
Pretty much.
So let's remember Nathan's question. Nathan's question is, how does a proton turn into a neutron? Awesome question. Can I just deal with that next time?
Yeah.
Because otherwise I'm going to start drooling over here, okay? All right.
Same.
Here's the important point. The important point is that there are three different forces in competition with each other here, and I want to spell them out for you. First of all, I've got an important question. Why is the center of the sun hot? Does anyone think they can answer that question? The center of the sun is at 15 million Kelvin. How'd it get that way?
Because there's nuclear fission.
That's what I thought you were going to say, and that answer is so freaking wrong. Hold on a
Because it's a
second.
bunch of gas compressed into a small space.
Kind of what Raph said, actually, but hold on. Sal, were you the one who said nuclear fusion?
It's fission, right?
No, it's fusion. Okay,
It's a
hold
fusion?
on.
Okay.
One second.
I don't remember the difference between the two, but it was one of the two.
I have a slide that was, that is supposed to address, I actually had a whole rant that was supposed to address that. Share my screen. Just a sec, buddy. Right here, slide 57. In nuclear fission, you take a big fat atomic nucleus, like uranium-235, you whack it with a neutron as if this was the cue ball, and it breaks apart into two daughter nuclei. In the case of U-235, the daughter nuclei are radioactive cesium and radioactive rubidium. You also eject some extra neutrons, and you create a gob of energy in the form of gamma rays. Think of fission as being related to fissure or a crack. You're cracking open the nucleus. Nathan?
I was going to say, is that kind of like forcing like a half-life to take place?
Well, half-lives are kind of part of this reaction. These nuclei don't have enough neutrons to glue their centers together. And remember how I told you that the strong force is a short-range acting force?
Mm-hmm.
When you try to glue a nucleus of this size together, the size of the nucleus is increasing to the point where the strong force can't effectively glue this thing together anymore because it's getting weaker over the radius of the nucleus, or the diameter of the nucleus. Now, the sun doesn't, this is what we power our nuclear power plants with, and a lot of nuclear bombs use nuclear fission. It's a very dirty form of nuclear energy because you get energy out, but it also releases these radioactive isotopes, and rubidium and cesium are themselves radioactive. Not helpful. The sun's energy is a clean form of energy. It uses fusion, and it fuses small nuclei into bigger nuclei. So you take just like small atoms like protons or hydrogen atoms, you glue them together into helium. Now you don't get quite as much energy out, but none of the byproducts are radioactive. If we could fuel our houses, if we could power our houses with nuclear fusion the way the sun did, we would instantaneously solve our energy crisis and we would also solve our climate change crisis because we would have an unlimited form of energy that was non-polluting. Obviously, we would love to do that. Why haven't we done it? Because you need fucking 15 million Kelvin worth of temperature in order to get those protons together. And the only place that actually gets hot enough for fusion to take place is the sun. We've definitely tried it in these machines called tokamaks. And in the 1980s, people had these big donut cylinders and they were trying to fuse hydrogen together like the sun does. And it was just taking too much energy. They couldn't hit the break-even point. I have a rant on that as well, but I'm going to save that for next time. Okay, so let's look at what's going on here. In speaker view, we're going to look at, actually, wait, I didn't address the fundamental point that I was talking with Sal. Sal, the reason why fusion cannot be the cause of the sun's central temperature is you would find yourself in a circular argument pretty quick. The sun needs to get hot enough for fusion, but fusion provides the temperature for the interior of the sun. So how do you ever start the cycle? Do you see what I mean?
It's a paradox.
Yeah.
It's a paradox. In fact, it makes you realize that fusion is not why the center of the sun is hot. Fusion happens.
It's a product.
It's a product, right? Raph, tissue's not in his nose anymore, actually had the correct answer. The sun's hot because of gravity and hydrostatic equilibrium. The star squeezes itself down and the gravity makes the sun hot. Let's spell this out as 3 bullet points here. The role of gravity in a star. Gravity is going to squeeze the star, and the squeezing of the star makes it hot.
Oh yeah, we did talk about this in class.
Right.
In the class time.
Then there's electromagnetism. Electromagnetism causes the protons to repel. That works against fusion. The strong force, if the temperature is high enough, the strong force is trying to glue the protons together, which then makes some extra energy. Okay, class. Now it's time to answer the question and to give me your best guess. If I leave gravity alone and I leave electromagnetism alone, but if I suddenly become Jehovah, or let's find if I could become Vishnu, I have to find some non-offensive deity. If I could become Odin and I could tinker with the machinery of the universe itself, and I could use the powers of Odin to suddenly make the strong force 10 times stronger, what do you think would happen to the temperature at the interior of the star? You've got 3 choices. A, nothing. B, it goes up. Or C, it goes down.
Well, if the strong force is what glues protons and causes the fusion, would the temperature... The gravity is squeezing it, which is causing the heat. Wouldn't the temperature go down?
Yes! Ding, ding, ding! That's the correct answer. In fact, paradoxically, a stronger strong force would make fusion easier, but that would actually allow fusion to happen at cooler temperatures, which is totally a mind F, right? Okay, so that's the correct answer. The temperature would drop. And now, along with me, students, we're going to write a little paragraph about this. Are you ready?
No, wait.
Sure.
So for the notes, so like when it says, wait, what? When it says hot, is that ratio under it? Or 15 times 10 to the 6th K?
Yeah, sorry, 15 times 10 to the 6th Kelvin.
Okay. 15. So that's
background. Oh my god.
hot. 15. And then the second one says ropes.
Oh, I'm sorry. Repels protons. I apologize. I was writing quickly.
This took about 23 minutes.
Repels protons. Gotcha.
Yeah.
What?
And then the last one says glues protons, correct?
Yes.
All right. And then, yeah, that's that. So 15 times 10 to the 6th. Okay, we can go.
All right. We're going to go into paragraph mode now. I'll try to keep my writing as neat as possible. This is going to be rough. If the strong force was 10 times stronger than it is today, then the central temperature of the sun would actually drop. This is because it is ultimately gravity that controls the central temperature of the star. And now we're going to talk about the strong force and what role it plays battling electromagnetism. A stronger strong force would allow the colliding protons to fuse at slower speeds and lower, let's say, or lower kinetic energies and thus lower temperatures. Let's write this new strong force could more easily overcome the electrostatic barrier of the protons. Can you guys still see all this? We're almost done. We got a little more to, okay. Dot, dot, dot.
We can't see the bottom.
Yeah.
Thought.
I'm going to have to
Hold
go back up to the top here. Let me get my pointer stick. Hold on.
I can type about 600 times faster than I can write, so
That's what I've been
Yeah,
doing.
it must be easier to type this
writing.
instead of writing it down.
I'm typing well before he even writes it.
That's what I was doing. I was typing it.
Yeah.
Hey, where are you guys?
50
I'm caught
times
up.
10 to the 6.
This new strong.
Pardon?
Hold on.
What does that word say? It says gravity that controls the what?
Central?
If you all open the chat, I typed it all.
Oh, really?
Oh,
There you go.
Thank you,
What a
Riker.
cool guy.
You are the shit. We're not done yet, though. I got our race to go back up to the top.
MVP Riker.
I understand there's more to be typed, but
Okay.
figure get
Yeah,
them caught up
Riker.
first.
yeah, Riker, you got this. I'm just going to take a photo when you finish.
I don't want to lose
I
my
believe in you.
thought momentum here, so let me know when I can continue.
You can go, I think.
How about everyone else? Can I continue?
I'm good. All the text is
you,
in chat.
with my permission.
All the
right,
text
so
is
you
in
got down
chat.
to protons, right?
You can
Yep.
go.
Riker, did you get this?
It's all in the chat. If anybody's missing it, it's all in the
Yep.
chat. Yes, I've got the
Is
whole
anyone
thing.
else? Yep.
Word for word.
Awesome. You are the best, Riker. Okay,
Anyone
let me
else
go back
in the chat?
let me just get back into my thought space here. The new strong force could more easily overcome the electrostatic barrier of the protons, and thus fusion could proceed and allow fusion to proceed at temperatures lower than 15 million Kelvin. In essence, what we're saying is gravity would not have to squeeze as hard. Gravity would not have to squeeze as hard to ignite nuclear fusion and the star would enter. And now it's time that we revealed what this problem is really about. This problem isn't even really about fusion, if you think about it. This problem is about hydrostatic equilibrium. And the star would enter hydrostatic equilibrium at a lower central temperature. I think that's about as complete an answer as we can imagine.
All right, hold on. I'm going to give everybody the full paragraph.
Some formatting would be nice. Although I didn't really do such a good job at formatting either, so.
Here, this is as complete an answer as I can give you guys.
Cool. This is going to be useful. Hey, Riker, don't let me forget to save this chat, because students who are tuning in later will probably greatly benefit from being able to read this. Okay?
Right. All right, so after the word protons, it's going to start the whole paragraph again. So just note that. It's going to say a bunch of it twice.
I sure hope the students watching the video later can see this chat that I'm clicking on. I've been trying to attach the chats to the videos in CCRI Medials, but it attaches the chats with this, even though I have a perfectly reasonable name for the file, like group chat for lecture 1225 or whatever, it changes the name of the text file to some indecipherable string of characters. So
if not, I'm typing the homework on my Google Docs as I go. If need be, I can share them on the Discord later.
Killer. Yeah, that's right. You guys set up a Discord for that. Thanks, Ivy. Thanks, Riker.
Riker, can you send me a Discord link in the chat?
Aren't you already linked?
Okay,
I don't
kids.
think so.
I'm going to embarrass
need the
myself
link
and ask
too.
a Grampy question. What the hell is Discord? I don't know what that
It's
is.
something
alright,
for
you know what Skype
favor.
is?
What's
Yeah.
that?
I think
Do you
it's
know what
something for
Skype
favor.
is?
I vaguely know what Skype is, yeah.
Alright, so it's like
It's like that
Skype,
almost.
but you can also make like
For everybody who's in the
a
astronomy
messaging
quarantine
thing
style,
with a bunch of channels.
for everybody who's in the astronomy quarantine style, once again, that whole paragraph is typed in there. You should just be able to copy and paste the whole thing.
Nice.
Oh yeah.
Wait,
That's
so
what I call learning right there.
Professor,
Yeah.
is this like this is what mine looks like? I mean, I doubt you can see it with like.
Oh, wait. Let me go into gallery view. All right. Well, it looks
This
like
is what I
usual
have.
submissions that I get from you guys, but that's cool, man. I dig it.
That's fine. All right.
I think it's about the time we're spending here together. But yes, that's going to be totally cool, Raph.
So are we submitting this in like
Blackboard.
similar to how we submitted the lab?
Yeah, if you go into the assignment under the homework tab, and at the end of this session today, I'll show you guys how to do that. Oh, Julio, I love your doggy. That doggy's real cute. Okay. The AS1020 students have a cat crew, so everyone holds their cats up. And so you guys are up to be the dog.
I don't have any pets.
Smart man. Pet your friends' pets. Go home to a clean apartment. That's what I say.
have a cat, not a dog. How do I join the cat crew?
We're going to work on that, okay? I think we're ready to move on to the next problem. That was a bit of a whopper, right?
Yeah.
I think.
You got this.
Yeah.
I'm about to erase. Does anyone want to object?
18 minutes or something.
Michael, I know one. Hey, guys, I can only go as fast as you guys can go. So
I'm good.
I'm about to erase.
I know.
Go ahead.
I know. All right.
Okay, we got one more whopper, and then the questions will be a lot faster. So let's get to the next one. What's the problem?
Number 50.
Solar energy output.
Hold on a second.
Yep. All right, everyone. The link to the Discord is in the chat.
Thank
If you don't have it already.
Okay. Riker, could you do us the honors? Hold on, let me just maximize my volume here. Oh, I am not as loud as I want to be here. Hold on. Okay. Riker, can you read me the next problem, please?
Sure can. Okay. Observations over the past century show that the sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 or more. Explain why changes in X-ray output can be so much larger than those in the output of visible light.
Okay. Explain why changes in the output of the sun's X-rays can be so much greater than the output in the sun's visible light. This is a question we are equipped to answer because of our first part of this lecture, which dealt extensively with X-ray emission from the sun. Class, I've got a question for you. What does the sun put out more of? Does the sun put out more visible light, or does the sun put out more X-rays? What's the answer to that question?
X-ray.
X-ray.
That would be a complete misreading of this question. That is 100% wrong. To understand why I said that, I first need to take you guys back to our PowerPoint slideshow. Remember that today I lost a significant fraction of time and screwed us up by having an extensive discussion of the energy output of the sun when I showed you this picture of the sun's radiation profile.
Oh, much more of it is in the visible light. Okay, now I'm seeing it.
Riker, do you see it?
I see
Riker's
it.
point, hold on, let me make sure everyone else follows you, Riker, okay?
Hold on.
Riker's saying, look where the peak of this curve is. The peak of this curve is actually smack dab in the middle of the visible spectrum, right around 500 nanometers. What color is 500 nanometers?
Hold on, I'm drawing a couple of lines for some markings for people.
Oh, cool. Wait, can you slide that over to the peak of the spectrum? Oh.
This is I
that's-
highlighted. That's the visible spectrum.
Whoa, you are so awesome, Riker. This is great. And now show them where the peak is.
The peak would be. I'm gonna use this small.
You know,
stamp.
your colors could have been more acutely coordinated. You could have put violet at 400 and kept red at 700.
I just went with what I had.
All right, okay, all right.
It peaks right here.
450, right?
I swear to God, I'll draw a smiley face.
Okay, I was using the theoretical black body. Whoa, I'm sorry, that's my bad. But, okay, you're using the real spectrum of the sun, which is noble of you. I was going to look at the theoretical, yeah. Or either one of those checks, good. But my point is the check is around 500 nanometers right about where green is in the visible spectrum, okay? Okay. Where would X-rays be, Riker, on this graph? Where are X-rays on the electromagnetic spectrum?
X-rays would be down by actually less than 200.
Like they're fucking over here in the barely even emitting at all. I don't get it, Riker. What the hell is this question asking me then? Like I thought the question said the sun puts out 10 times as many X-rays as visible light. What's the question really asking?
No, it's asking why the X-ray output can be so much larger than those in the output of visible light. Why it can vary. No, hold on. Why it can vary more than the visible light spectrum can.
There you go, buddy. That's what I was looking for. It's about the variability. Okay. Let's make a little graph explaining what me and Riker were just talking about, and I think this should be part of your answer, so follow along with me. We're going to make a little graph of the sun's output over the last 100 years, showing X-ray and visible light. So first what we're going to do is we're going to take a ruler and we're going to make a y-axis, and then we're going to make an x-axis. And the y-axis is going to be the intensity or the brightness of the sun's light measured in watts per meter squared. And on the x-axis here, we're actually going to do time in years, with this being the year 1900, and over here being the year 2000. So that's observations over the course of a century. Now, we're going to use black in my cartoon for visible light. And because X-rays are short wavelength on the blue end of the spectrum, I'm going to use blue for X-rays. First, we'll draw in the visible spectrum, or the visible energy output, showing microscopic little wiggles, but overall the sun's visible light output remaining constant, with these fluctuations being at the level of approximately 1%. Now, students, before I go any further, they told us that the X-rays vary not by 10%, but the X-rays vary by 10 times. Students, if we want to compare these in the same unit scale, what is a factor of 10 as a percentage? Okay, what is 0.5 as a percentage?
5%.
Half.
Oh, that's 50%.
50.
Right.
What is the number 1 as a percentage?
10%.
100.
100%.
100.
What is the number 10 as a percentage?
1,000%.
There you go. Now you guys are with me. Okay, I just wanted to point out that the fluctuations in X-rays are 1,000 times greater than the fluctuations in visible light, and yet, as Riker demonstrated, the X-rays are clearly much lower in flux, but they're more variable. So here I'm going to draw lower X-rays, but a higher variation along with those X-rays. See that? Where the peak can be a factor of 1,000 times greater than the minimum, right? It's a factor of 10 times. Well, I should get rid of it. It's a factor of 10 times. I shouldn't do this. That's not helpful. That makes it look like it's 1,000 times greater. All right. Now it's time to glue all the pieces together. What layer of the sun produces visible light?
The photosphere? Is that right?
That's correct, Raph. What layer of the sun produces X-rays? Oh.
That's the corona, isn't it?
Yeah, very good. Do you guys remember when I showed you those really cool pictures of, or that video of the sun? Like, let's go here to the Solar Dynamics Observatory again. You guys can see my screen, right?
Yep.
Yeah.
He hides his. What? I'm the one in class.
What's that?
No,
No,
this
he's
is
talking
talking
to
to my
someone.
mother.
That's what the sun looks like in X-ray light. What layer of the sun are we looking at? Riker, you had it correct. It's the corona. Hey guys, I want to point something out to you. Let's look at the sun right here for a second and freeze it. You can actually see the photosphere in this picture. What color is the photosphere of the sun in this picture?
Black.
Yeah, it's black because the surface of the sun isn't giving off any X-ray light. Where do we see the X-ray light coming from?
The corona, the outer edge of the sun.
But in particular, this is a color coded by intensity of sunlight. I'm sorry, intensity of X-rays. Where do we
From
see?
the solar flares?
Or
something like
yes,
that?
or where
What
the
are they called?
magnetic field strength becomes the most intense. Do you see this?
Okay.
This is a dipole magnetic field loop. Notice where the magnetic field lines converge, you get really, really bright emission of X-rays. By the way, does anyone remember what type of emission this is called? The fancy term for this?
Crap.
I bet Anakin does. Anakin, do you remember what this is called? I don't know. I'm putting Anakin on the spot
Hold
here.
on. I know this. Crap.
As in the emission spectrum or like the coronal mass ejection? I mean, what?
No, I meant the process that produces these X-rays.
It's the one oh wait, no.
Oh, wait. Oh,
The
man. I know
rubber
what you're
band
talking
thing?
about.
Yes.
The rubber band thing where the
Kind of.
magnetic field, I remember the magnetic field gets wrapped around so tightly and builds up tension then snaps.
Well, yeah, that's what's causing the eruptions, but the emission of X-rays is a more microscopic process known as...
Oh, my God. I think I know this. I forgot. I know what you're talking about.
Someone drew on my screen. All right,
Is it the Bremsstrahlung?
Yeah! Was that Hope?
Yeah.
Yeah, I was off. Never mind.
Bremsstrahlung radiation. So here's the picture of Bremsstrahlung radiation. It's a particle. These pictures aren't great, I know. A particle strikes them. Is this a GIF? That would be really cool if this was a GIF.
Yeah, I got it.
Oh. No, it's just a movie that does fucking nothing. Thanks for nothing. The particle strikes... All right, you know what? This sucks. This is terrible. I was hoping to find a really cool picture of Bremsstrahlung, but there's a reason why I have to draw this. I haven't found a really cool animation of Bremsstrahlung. Basically, the free particle strikes a magnetic field, and it ends up emitting a photon, an X-ray photon. Oh, I know. Remember I did my physics Java apps?
Yeah, I remember a little bit.
Hold on. I feel compelled to do this for some reason. How do I? S drive, physics Java apps, rating charge. This is the Bremsstrahlung radiation, right? You take a charged particle, you speed it up to a relativistic speed like 80% the speed of light, and then when the particle strikes a magnetic field line, boop, it stops. And did you see that little kink in the field line?
Yep.
That was a super short wavelength, super high energy photon called an X-ray. So that's Bremsstrahlung, except they don't show the magnetic field here. There's your field line being emitted. Okay, whatever. So, okay, another question for the class. Stop share, speaker view. Fine, if X-rays are produced by Bremsstrahlung, there's two letters in there somewhere, but I don't know where it might be two S's or something. What about, oh, sorry. Let's do this right. X-rays are produced in the corona by Bremsstrahlung. What is producing visible light in the photosphere? Hot shots? I'll give you a hint.
Thin gas.
Photons?
I'm talking about photons. What produces the light from the photosphere?
The emission spectrum.
False.
Black body?
Thank you, Morgan. It's a black body spectrum,
Oh.
right? Did you know that the gas in the photosphere is roughly 1/10 the density of air in this room? The photosphere, the surface of the sun, is more tenuous gas than the air in this room. And even still, at 1/10 the density, it still produces a black body spectrum, just like this little candle does here, or this lighter. This lighter is a black body spectrum. That is white light. It's a complete rainbow. There are no breaks in it. I think you're ready to learn and to glue it all together, okay? I'm going to erase this and we're going to write our paragraph. No, Raph can't handle it.
No, hold on. I gotta do that
Hold
extra
on one
one.
second, too. I'm still copying.
Sure, take a second.
I'm also ready to type, and I'll share it all again.
All right, we appreciate
Yay.
that.
Wonderful weather we're having.
Yeah.
It's all right.
Yeah, it's
I gotta
not
see
bad
if the
outside.
sun is up.
Yeah.
Make sure you wear the
it's-
glasses if you look for it.
Okay. Raph, can I erase yet, or?
Yeah, you can. Yeah.
I'm good, too.
Okay. I'm about to erase. Speak now or forever hold your peace. Okay. So let me remind myself the question again. I just want to read this one more time. Observations of the past century show the sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 times. Explain why changes in X-ray output can be so much larger than those in the output of visible light. Okay, we will write changes in the output of X-ray emission are so much more variable than changes in visible light, because X-rays are produced in different layers by different processes. Okay, that's our opening salvo. And now we're going to get into the different layers and the different processes. So far, so good?
So far, so good.
All right.
Wait, so it says X-rays are pinhead, right?
Our what?
Different. That one, yeah, that. What's
X-rays
that?
are produced.
Oh, produced. Okay.
Did you say pinhead?
Yeah.
Yeah. I can't listen and write for some reason at the same time. I don't know why.
Well, these are challenging times that we're living through here. Okay, so I'm going to continue on. X-rays are produced in the sun's corona by interactions between charged particles and magnetic field lines. as the magnetic field lines fluctuate with changing magnetic storms and the sun's 11-year solar magnetic cycle. And that's a key buzz phrase right there. I'm going to underline this, the sun's solar magnetic cycle. It has an 11-year period. As the magnetic field lines fluctuate with changing magnetic storms and the sun's 11-year solar magnetic cycle, so do changes in the X-ray output vary. Make sure I got this. Particles. As magnetic field lines fluctuate with changing magnetic storm. That word is storms. And the sun's 11-year solar magnetic cycle, so do changes in the X-ray output vary. I think that covers our X-rays. Okay, now let's address the visible light. Riker, I'm going to have to erase up here at the top. Is that okay?
I got the whole thing.
All right.
I type as you speak.
Awesome. Visible light, on the other hand, is produced at the sun's photosphere by thermal blackbody radiation. As the sun's photosphere remains constant at, does anyone remember the temperature of the sun's photosphere? Throwing in details like this always impresses your professor.
15 million Kelvin.
That's the central temperature of the sun.
Okay, my fault.
Surface temperature of the sun. It was in our constants of.
Is it? Oh, I don't know in Kelvin.
What is it in Fahrenheit then?
It's like 9,000 degrees.
No.
5,800 Kelvin.
Thank you. Okay. 5,800 Kelvin. Does that translate
Definitely
to 9,000
look it up.
degrees Fahrenheit?
Were
you making shit up, Michael?
I think it's like 9,000 degrees.
You could be right. Hold on. 5,800 Kelvin to Fahrenheit. Yeah. 9,000, well, 10,000. Okay, but kudos to you, man. Kudos to you. What, do you know that from Trivial Pursuit or something? Or what?
No, I don't know if you realize this. I'm just like really intelligent. Like,
I do realize that, actually.
It's always good to be modest.
Yeah, right.
Yeah. I'm
As
humble.
the sun's
I'm humble.
photosphere remains constant at 5,800 Kelvin, so does the output of visible light remain constant with only a 1% variation due to blank. What do you guys suspect is causing the 1% variation in the sun's visible light output? I wonder what could do that. I wonder what could possibly, what could possibly be affecting the visible light output of the sun at a 1% level? What would be capable of blocking sunlight? Just tiny little bits of visible light at the photosphere.
Sunspots?
Oh, hell yeah, that's right. Sunspots, with only a 1%
Crazy.
variation due to sunspots. Nicely done. You are really intelligent, Michael. You have all of our answers.
Don't put that on me. Don't put that.
All right, that's cool. Guys, those were the really hard problems. I know we took a lot of time doing them, but they were sophisticated questions that required sophisticated answers.
All right. Well, there's the full typeouts in the chat. I will put it all in the Discord as well.
Cool. So I just want to show the studio audience at home that we have the entire thing here, both the strong force and the, Riker, you know what would be kind of cool? Could you put the numbers of the questions in front of those?
Yeah, I should be able to edit them.
Well, actually, no, if you can't edit them, that's okay.
Well, I can edit the Discord one so everybody
You know
knows
what?
which ones they
If
are.
someone's watching this at home, or everyone's watching this at home, if someone's watching this later, then they'll figure it out. They got to. That's their job.
It's their problem.
They got it.
I can edit it on the Discord for anybody who's doing it now, though.
Okay.
Or later.
Julio, what's your dog's name?
On the Discord looks at it.
Elliot.
Elliot. You got that, Elliot? Wait till Elliot sees some videos of the raccoon that I've been feeding. There's a raccoon that lives in the sewer near my house.
I fucking love that raccoon.
Oh, have you seen it? Yeah.
Yeah.
Last night I tried to go fishing for raccoons, and my friend and I, we attached a cookie to the end of a dowel, and I opened up the window, and I was dangling the cookie on the string out the window, and the raccoon, he was looking at it. Maybe I'll show that to you at the end. I couldn't get him to come out of his hole, but
I think I remember at one point you said, don't bite me like last time.
he bit me. I had a big rubber glove on, but I was pretty freaked out because that could have been a serious trip to the hospital.
Yeah.
Let's see here. All right, we should go on to the next question, but real quick.
What is going on?
Oh, hold on. Wait a
Have you
second.
named the raccoon?
Yeah, the raccoon's name is Buff. I first have to delete.
Why Buff?
Huh?
Because he's super strong.
What's super strong?
Buff.
Actually, I have the sneaking suspicion that you've fed it so much that it's too fat to get out of the sewer.
No, he comes out of the sewer. I see him all the time. The reason why I named him Buff is because Buff Chase is the downtown real estate developer who owns all the buildings in town. And I was thinking that this raccoon is kind of like the king of downtown.
Cute.
All right, I'm wasting everyone's time. I don't even know why I'm doing this. Okay, so
I don't think this is a waste of time. I think this is very valuable.
Apt analysis, sir.
Personally,
Apt analysis.
I've got all day, so I'm not in
All right.
any rush.
Yeah, I guess we're not going anywhere, but let's get the work done first. I had a really great video of me feeding the raccoon, but I couldn't find it. There's too many stupid pictures.
Nah,
Okay,
I got work. Not soon, but like soon, you know.
let's get on with it. What's our next question?
Chemical burning and the sun.
55.
Number 55. When an object burns in a fire, the amount of energy released through the chemical burning is typically about 10 to the 8 joules per kilogram of mass burned. Use this fact to estimate how long the sun would last if its energy source were a huge fire releasing chemical energy, rather than its actual source, fusion energy.
Okay, so
Am
the
I
question
allowed to
is,
guess
how long
first?
will the sun last as a ball of fire?
I'm gonna guess 4,000 to 5,000 years. That's my guess.
It's pretty close, actually. So we're going to need some values to get this going. We're going to need to know the mass of the sun, which is 2 times 10 to the 30 kilograms. We're going to need to know the luminosity of the sun, its energy output.
4 times 10 to the 26 watts.
Thank you. All right, what do you think we should do?
We got to convert something, right?
Yes.
Using dimensional analysis.
Yes, that's what I want to hear. So let's start with 10 to the 8 joules per kilogram. Hey, what do I want my final answer to be?
Some unit of time.
Yeah, we want some unit of time. So we need to figure out, where am I going to get time from kilograms, watts, and joules per kilogram? That's kind of weird.
Isn't watts the same as per second or something?
It's what per second?
Meters per second squared?
No.
Per second.
Oh, what is
Morgan?
Joules
I
per
have it in my
second.
book.
Morgan remembers that watts are joules per second. Excellently done, collective mind. We're going to get our time from the watts. Okay, so
You're
let's
a
make this
hive mind.
big dimensional analysis problem. We've got joules per kilogram, and we need to multiply by some things that are going to kill kilograms and kill joules and end up with seconds. Let's do the units first and the numbers second. Someone help me? Sorry, I'm spacing out here. Guys, look, you've got joules per kilogram. Well, let me rewrite this. I have 1 times 10 to the 8 joules per kilogram. I need to multiply by some units such that I end up with some number of seconds. What does dimensional analysis tell me I need to do? Let the units do the walking.
Convert it to joules per second.
Put joules on the bottom.
Put joules on the bottom, and what goes on top?
Kilogram?
No, we already used up our joules per kilogram. The energy, the kinetic energy is, I'm sorry, the energy contained in chemical reactions releases about 10 to the 8 joules for each kilogram of chemical reaction. So we can't use a conversion from joules to kilograms because we started off with that. We have to look at the other 2 pieces of information we have, the mass of the sun and the luminosity of the sun. Use their units and jiggle them around until you kill everything off. I'm confused, guys. I can't figure this out without your help.
You liar.
I would never do such. I would never lie to you like that.
Put seconds over joules.
I'm sorry, Morgan?
Put the seconds over joules.
Yeah, Morgan's saying let's use the joules per second and reverse them. So we'll put seconds on top. That gives us our seconds here, right? And put joules on the bottom to cancel out our joules. What else should we do, Morgan?
And then on the other one, just put kilograms on top.
For the mass of the sun. Hey, awesome. All right, so now Morgan, help us figure out what numbers should go in here. What numbers should I put in?
Put the 4 times 10 to the 26 next to on the bottom where the joules is.
Yes, correct. And what goes on the top?
1.
That's right. The sun releases 4 times 10 to the 26 joules in 1 second. How about over here?
Put the 2 times 10 to the 30
The
kilograms.
mass of the sun. Okay. Very good. Do you notice that we didn't even have to really use our brains to think? We just had to use dimensional analysis. You multiply the mass of the sun by the energy released per kilogram, and you divide it by the luminosity of the sun. What does that give us, by the way?
Where's that calculator?
Ask the question again. Sorry.
It wasn't a question. It was more of like a command. It was take the mass of the sun, multiply it by the joules released per kilogram in chemical reactions, and then divide it by the luminosity of the sun. Do you guys have your Casio calculators or what?
5 times,
I don't
5 times 10 to the 11th.
Someone else can do this.
That's what I had, so.
Okay, that's our answer. 5 times 10 to the 11 seconds. But we should try to make some sense out of that by converting it to years, right? Do any of you know the number of seconds per year? Because that would speed this job up.
Let's see, there's 525,600 minutes in a year.
Oh, what are you
I'm
singing
60.
the Rent theme song again?
Yes, I am actually. Don't
Okay.
you judge me.
How do
I would
astronomers
never.
remember the number of hope?
I can't. It's something with pi, but I
Yeah,
can't
right.
remember.
There's 31,536,000 seconds in a year.
1 year for astronomers is approximately pi times 10 to the 7 seconds,
Yeah.
right?
Okay.
All right, so it's 5 times 10 to the 11 seconds multiplied by 1 year over 3.15. It's close to pi.
Wait, why is there a 7 on top of the 10 over on the one above that right there? It says 1 year cubed times
No,
L equals.
approximately equal to.
Oh, okay.
Yeah, this is the mathematical symbol for approximately equal to.
Yeah, okay. And then it says pi times 10 to the 11th, not 7, right?
No, it says 7.
Oh, okay. Okay.
Am I writing too
Wait.
slow?
A little bit.
No.
Yeah.
I'll make it better. Oh, I'm supposed to be in speaker mode. I'm sorry. Jeez.
That's okay. So wait, so how did it turn into, oh wait, never mind. I know how, never mind. And that says 3.15 on the bottom. there?
3.15, yeah.
Yeah.
Close to pi.
Did you guys already get the answer for that?
No
Yeah.
one.
Sorry, what is it?
16,000.
And isn't it like 15,873 years?
15,000. All right, whoa.
16,000.
Approximately 16,000 years.
Thank you. Thank you.
Oh, just 2 sig figs?
Yeah, I mean, look, you only got one going into it, bud, so let's not get crazy.
Okay.
Thank you, Sal. I spaced out for a sec. All right. We ready to move on?
Yep.
Yeah.
All right.
Yeah.
What is the next question?
56.
56? Oh, good. I'm not looking very far.
Hope, can you read that for me?
I don't have my book.
I got it.
With me.
3-point question here. The lifetime of the sun. The sun's chemical composition was about 70% hydrogen when it formed and about 13% of its hydrogen was available for eventual fusion in the core. The rest remains in layers of the sun where the temperature is currently too low for fusion. Part A. Use these data and the sun's mass to calculate the total mass of hydrogen available for fusion over the lifetime of the sun.
So we're going to do the same question we did before.
Professor, can you angle that? Okay, thank you.
Okay. Let's first find the total mass of hydrogen available for fusion, okay? Let's take the mass. Well, how do we get the mass of hydrogen? We have to get rid of the helium, right? So here's the sun. Roughly 3/4 of it are helium, and we got to exclude that. And only the inner 13% of the core is hot enough. So we need to calculate the total mass of that fraction of hydrogen, which can be used up. Right? In other words, we just take a couple percentages, right?
Yeah.
So take the mass of the sun, 2 times 10 to the 30 kilograms. How do we get rid of the helium? We have to multiply it by what percentage?
By 0.7.
Yeah. And then how do we reduce that further to just a percentage that's hot enough for fusion?
Times 0.13.
Yes. All right, punch them up.
I have an answer if anybody's ready for it.
I'm ready for it.
All right, I got 1.82 times 10 to the 29th.
I'm just going to keep 2 sig figs.
1.8? Okay.
Units?
Kilograms.
Okay. Now, what's going to control the amount of lifetime the sun can put out is the amount of light that it gives off every second, right? What quantity expresses the amount of radiation that the sun puts out per second?
That's not the number I'm getting.
Oh.
4 times 10 to the 26 watts.
Anakin, what did you get?
4.2 times 10 to the 29th.
4.2 times 10 to the 29th? Okay. Can I get a third person? Do I have to do this, or can I get a third person to confirm it?
I actually got 1.82 times 10 to the 29.
Same here.
Uh-oh. Uh-oh.
2EXP30
Here we go.
times 0.7 times 0.13.
I'm so scared.
Anakin, well, how are you getting the 4 instead of the 1.8? I got 1.8.
I'm doing point. Oh, I was doing 0.3, not 0.13. That's why.
Oh, okay. All right. That's okay. Many hands help keep us from making errors here. All right. But anyways, back to my original question. What about the radiation from the sun's surface? The radiation is what causes the sun to lose energy and eventually run out of fuel. So what parameter of the sun describes its light output?
Luminosity.
Right. So the mass available for fusion is 1.8 times 10 to the 29 kilograms, but the luminosity of the sun is 4 times 10 to the 26 watts, which is 4 times 10 to the 26 joules per second, right? Wait a minute. I'm sorry, what was the question part? I'm getting confused. What is the question for part A?
Use this data and the sun's mass to calculate the total mass of hydrogen available for fusion over the lifetime of the sun.
Sorry. Okay.
So That's part A.
So we're done with part A. Sorry. What's part B?
Part B, the sun fuses about 600 billion kilograms of hydrogen each second. Based on your result from part A.
Wait, how many zeros are in a billion?
9.
Okay, keep going, Riker.
Based on your result from part A, calculate how long the sun's initial supply of hydrogen can last. Give your answer in both seconds and years.
Look at the units. Do you guys see what to do? What do I do?
Microanalysis.
Okay, I like it. How do I do it, Morgan?
Conversion. Dimensional analysis.
Yes. So tell me what to do then.
If
All
I
right, so
can-
you, okay.
Morgan,
you
go
can
ahead.
Okay, so you times it by a division bar.
What's it?
The 600 times 10 to the 9.
But Morgan, won't that put seconds on the bottom? I thought I wanted to end up with quantity of time at the end. I don't want to end up with per seconds. You see my point?
Yeah, you put the seconds on the top. And then the kilograms on the bottom. And you times it by the kilograms on the top.
Okay, so tell me what to write.
1.8 times 10 to the 29 kilograms.
Okay.
Times of division bar of seconds over kilograms.
Bless you.
And then this 600 times 10 to the 9 on the bottom of the book.
And what do I put on top?
1.
Very nicely done. Now compute it for me.
Three times 10 to the 17 seconds.
Nicely done. We should convert that to years, right? What's my conversion factor? What's my conversion factor?
3.15 times 10 to the 7 seconds over 1 or below 1 year.
Nice. How many years does that give us?
Okay.
Oh, there's another dog. Bella, you got a doggy too. Yeah, dog crew. It's dog crew versus
I got
cat
one
crew.
too. I got a
Me too.
dog here.
My
I
dog.
have 2 dogs.
I got
that were
3.
cleaned.
Oh, let me
Oh
filter.
man, look at that. Hey guys, at some
I
point,
got 3 of them.
we got to get a picture of everyone with their dogs, and then I'm going to show this to the Astro 1010 class, and I'll get a picture of them all with their cats. It'll be dogs
Cat,
versus
no
cats. Oh, that'll be so good.
Oh, so
Wait, I can't see
I
the
have
board.
a cat, not a dog. I'm in the wrong class.
I think so,
I-
yeah.
My dog just lays
Also
down.
only have a cat.
She's a cuddle bug though.
I'm a gecko, so I mean.
Okay, maybe it'll be everyone with their, and I got to get the raccoon, right? And I'll get the raccoon in the
you have to
photo.
find Buff.
I'm sorry?
You have to find your raccoon and drag him out of his hiding spot.
I know, I wanted to show you guys a video of him. He's really, really cute.
What about possums?
Well, those things are nasty looking. Have you ever seen a possum up close?
Well, it depends
Not
on
up
which
close.
possum you're talking about. Are you talking about American possums or Australian possums?
Talking about the one that you'll find like in your driveway when you're coming home from like a late night out, you know?
Yeah, those are scary. Australian
That's
possums
called a
are cute.
hallucination wrap.
That's what that is. Oh,
All right, okay, come on, wait, let's get back to it. How many years have we got here? How many years?
I thought it was a homeless person, but.
All right, come on.
Jeez Louise.
Look at that.
There he goes.
It's your job to calculate.
Stop.
9.5 billion.
Nice. 9.5 times 10 to the 9 years, or about 10 billion years. Question C, Riker.
1 second. Don't erase that bottom section yet. Okay. I just trying to make sure everything's clear for when I hand this in.
I do appreciate that as the person who has to look at this crap afterwards.
Right. Given our solar system is now 4.6 billion years old, when will we need to worry about the sun running out of hydrogen for fusion?
What do I do?
Professor, can you move the camera up a little bit? Because I can't really see. Okay, perfect.
In part B, we found a total lifetime of 9.5 billion years, right?
Yes.
So this is the one time in our class we'll ever use subtraction. Normally subtraction is for zeros, but here it comes in handy. 9.5 billion years minus 4.6 billion years equals what?
All right, now this math is getting kind of crazy. So
4.1 years.
Sorry, did you say 4.1 billion?
I said 4.
we have 4 years left.
Oh no.
Okay. That was my bad. 4.1 billion. My fault.
You have 4 years left to live. That's right.
We're all gonna die.
Yes.
The book was predicting it all along.
Oh yeah, the coronavirus.
The writers
Class,
knew.
I know the quality of my
4.9,
video.
right?
I want you guys to know that the quality of my video camera is obviously really crappy because I found this attached to an old computer at work. However, I shelled out some big bucks to get a fancy new webcam that has high resolution. So I'm hoping starting next week, our videos and our note-taking is going to be greatly improved on my end, okay?
How much is that?
I had to pay double what it normally costs because, believe it or not, right now there's a run on webcams, obviously. So, like, everyone was sold out, and I had to go to a price gouger, and oh, shit, a bee just got in here.
Uh-oh.
No.
I opened the window.
I hate bees.
He's over there, so watch out for him, Jordan.
Yeah, I'll watch
All right.
Wait, it would be 4.9 billion.
I'm allergic to them.
Yeah, I was. Guys, 9.5 minus 4.6 is 4.9, right?
That's it. I'm losing my touch with math.
All right. I think we're done, right? We have one question left.
I'm actually lucky.
Yeah, only one.
61.
I got a webcam just before all this happened.
That was smart of you. Yeah, your webcams look way better than mine. Mine is really, really shitty.
I'm just using my phone.
Mine was only like $20.
I mean, I could see the board good. It's not like bad, but like you could tell there's a little bit of blurriness.
Yeah, when I look at these videos later on YouTube, they look so horrible to me. But this is all I've got to work with right now.
Get 4K videos going. We'll get a Patreon and then have everyone chip in that wants to see this premium content.
That is so kind, but I actually already shelled out $150 to get it's not 4K, but it's 180p, so that's going to be something.
That's even better, yeah.
No, that's worse.
Well, that's actually
4K is better than
that's
180p, right?
yeah. No, well, it's better than this, so yeah.
It's way better than this. Okay, can I erase, or are you still copying, guys?
You can go.
I'm good.
How do you go down? Do that. No, go back. That's a punishment.
Sorry, Bella, did you say don't erase?
No, I was talking to my dogs.
Oh, okay.
Sorry.
Okay, all right.
What is the last question?
61.
61? All right.
Well, let me close the blinds because they're creating too much glare. Sorry, I opened the window to get some air in here, and I let a bee in, and there was glare. Okay. 61, right?
Yep.
What happens in 61?
Estimate how much mass the sun loses through fusion reactions during its 10 billion year life. You can simplify the problem by assuming the sun's energy output remains constant. Compare the amount of mass lost with Earth's mass.
So just one part?
Yeah, just one part.
Okay.
Okay, guys, this is a problem that if you don't have a tour guide for, can be a little complicated to understand, but it's a short, simple question. Let's draw a little picture together. Let's draw a picture of the sun. And the sun is losing energy through radiation. At its surface, that comes out mostly in the form of visible and infrared light with a magnitude of 4 times 10 to the 26 watts. So here's the energy of the sun being lost. Now, Albert Einstein taught us that energy can be converted into mass and mass can be converted into energy through that iconic formula E
equals mc squared.
And E equals mc squared is the basis for fusion. Inside the core of the sun, where nuclear fusion can take place, mass is being destroyed and it's being converted into energy in the form of short wavelength gamma rays. You'll remember that the fusion cycle called the proton-proton chain produces gamma rays as the primary energy output. All right. I'm going to make an argument with you guys. If the sun, where's my pointer stick here? Hold on. If the sun is putting out 4 times 10 to the 26 watts at its surface, it has to be losing or converting 4 times 10 to the 26 joules per second at the core. And the reason why I know this is because the sun is in equilibrium. And walk through the argument with me if you can. If the sun produced more than 4 times 10 to the 26 watts at the core, but only emitted 4 times 10 to the 26 watts at the surface, there would be more energy generated inside the sun than leaving its surface, and energy would have to be lost somewhere along the journey. We know that energy does not get destroyed. Conversely, if the sun produced less than 4 times 10 to the 26 joules per second at its core, you'd somehow have to make more energy on the journey from the core to the surface. But only the central core is hot enough to generate energy. That doesn't make sense either. The only thing that does make sense is that the sun is in a complete state of equilibrium, where the energy released at its surface is completely balanced by the energy converted in its core. With that in mind, let's do a conversion of E equals mc squared for 1 second inside the core of the sun. So in the core, in 1 second, the sun produces an energy of 4 times 10 to the 26 joules. What would be the mass lost in 1 second? It would have to be, take your E equals mc squared and solve for mass. Mass is E over c squared, or 4 times 10 to the 26 joules divided by 3 times 10 to the 8 meters per second squared. Shoot, hold on. Can you guys read that?
Can you just read what it says real quick?
4 times 10 to the power of 26 joules divided by 3 times 10 to the 8 meters per second square thereof.
I got 1.3 times 10 to the 18th joules per meter per second squared.
That sounds a little bit high to me because I know that if I square 10 to the power of 8, I'll get 10 to the power of 16, and 26 minus 16 is 10. That's many less orders of magnitude than you got. I suspect that you forgot to square your... Or you might have forgotten to
I
hit...
did forget to square it. Yeah, you're right.
Okay. Anyone else get something? Or try again, or Sal, whatever?
I mean, I did, but I don't think it's right.
Well, do you know what the right answer is?
Well, the answer I got was a bunch of 4s.
That's what I got.
Yeah.
Okay, unfortunately, I don't speak a bunch of 4s. I speak
It would
scientific
be,
notation.
I think, 4 times 10 to the 9th. Is that right?
Yeah.
That sounds good. We'll make it 4.4 billion then.
4.4 times 10 to the 9th.
What are my units?
Joules per meters per second squared.
Okay, but fine. Tim, yes, but a joule resolves itself into what?
That was Sal, by the way.
Oh, sorry.
It's okay.
Think about the kinetic energy formula. 1/2 times mass times velocity squared. A joule is a kilogram meter squared per second squared, and you're dividing it by a meter squared per second squared.
So it'll just be kilograms?
Kilogram.
All right. But keep in mind that this is the kilograms lost in just 1 second, correct?
Yeah.
We considered 1 second. So in general, we can say the following statement, that the fusion loss rate is about 4.4 billion kilograms per second in the core of the sun. How do we figure out the total number of kilograms that the sun will lose over its entire lifetime?
So would we convert? We would find out how many seconds are in its lifetime and then multiply it by that number.
Right, so we'll start off with 10 billion years, which is what it suggested, right?
Mm-hmm.
What's your conversion from years to seconds?
Approximately, well, 3.15 times 10 to the 7th.
And now we'll multiply that by 4.4 billion kilograms per second. Right?
Is this a part of the problem? Is this a part of the problem?
Sal, yes, this is the problem. If you remember the question said, please calculate how much mass the sun will lose over its 10 billion year lifetime.
Oh, okay.
So we're converting 10 billion years to seconds, and we know how much mass it destroys every second. So if we multiply the total number of seconds by the mass destroyed per second, we will get the total amount of mass destroyed.
1.4 times 10 to the 27th.
Which is approximately the same as the mass of Jupiter. The sun will destroy a Jupiter's worth of matter. Well, not really destroy it. It will convert a Jupiter's worth of matter into gamma rays during the course of its lifetime. Let's compare that to Earth, which was our final part to the problem. I'm erasing down here, class. The mass lost as a ratio of the mass of Earth is 1.4 times 10 to the 27 kilograms over 6 times 10 to the 24 kilograms.
Wait a minute. Didn't we say Jupiter can fit, what, 50 Earths?
Well, kind of. No, it's a no. Well, do you mean size or do you mean mass? It's 1,000 either way. 10 to the 27 is 3 powers of 10 greater than 10 to the 24, right?
Okay.
233.
230 Earths. The sun will destroy 230 Earths of matter in the form of hydrogen gas and convert it all into gamma rays, which eventually will leak out as sunlight and make its way down to your sunny afternoon. Now, this completes our homework. Yay. I know this was a tough one, guys. The sun homework was pretty rough.
He said sunny afternoon. I get it.
So, but what part of that question do we like?
I'm sorry, Morgan. Could you say that one more time for me?
What part of that question do we box off as the final answer?
Oh, this and this. I just want to see if the sun.
question.
Equations in the Discord.
I have a question. So
Yeah.
after like the sun's emitted everything, does it just go dark or does it like explode or something?
Well, in some ways, my friend, that is the answer to this entire course. Or the entire course is kind of about these sorts of questions. But I have a quick picture that I can show you that will explain it. And it won't take long here to show it to you. The sun weirdly expands when it runs out of nuclear fuel because the fusion temporarily goes a little nuts inside the center here. Hold on. Slide 5. This is kind of what's going to happen here. Let me just box. When the sun runs out of its nuclear fusion 5 billion years from now, can you guys see my screen?
Yeah.
The sun's radius will expand into a red giant. Some people, it'll certainly swallow up the planets Mercury and Venus, but depending on which calculations you use, the radius of the sun will actually come right up to the edge of the Earth and just cook it into a burnt cinder. Or the radius of the sun may actually swallow the Earth, and our entire planet will get swallowed inside of the belly of the star.
Yay.
I know, and that'll go on for almost 1 billion years more. But then eventually the star actually puffs itself to death in a giant smoke ring called a Planetary Nebula. And this is a picture of the Ring Nebula, which was once a low-mass star like our sun. And as the radius expands, it eventually kind of just blows itself apart into a gigantic puff of hot ionized gas, which then disperses out through the galaxy. And part of the things we're going to try to do once we're finished with the sun is take our knowledge of the sun and apply it to other stars and kind of calculate and imagine what's going to happen to these things as they run out of their nuclear fuel. And some of these planetary nebulae are quite beautiful, my friends. The Cat's Eye Nebula is another example.
Wait, what's this nebula? Hold on, I have this poster with nebula on it or something.
Let me go to gallery mode, and you can show me. Where's your poster, buddy?
Right there.
That looks like the Orion Nebula. I think that's a star-forming region. So that nebula is what happens long after that. That looks to me like the Orion Nebula, and that's where stars are being formed. Now, planetary nebulas do happen inside there as well, but you're looking at a very, very vast volume of space, and that bright central region is probably the trapezium. I think that's the
Oh,
Orion.
right there.
Yeah, that's called the. There's 4 stars there. I actually took a picture of that nebula too, although mine is a little more humble than yours. Our picture from the Jacobi Observatory. Jacobi Observatory photos. Oh shoot! Hold on.
Wait, can I see the board as well? Or when you're done, at least.
Oh.
I don't know.
Yeah. No, that's what I should be doing here. So.
What's the? So does that say on? So there's the M with the plus under. What's the one on the top say?
Mass lost. So I used the subscript LOST as this is mass lost diffusion.
Yeah, and then it says. So then when it says equals 230 Earths, correct?
Yeah. Or 230 times that of Earth.
Okay. And I think it's good now. Okay, thank you.
Okay.
Yep.
Well, the sun did not come out in between the 2 buildings. I was hoping to show you the photosphere. So instead, I suppose I'll just have to show you guys a raccoon video and then we'll end class. Do you want to see a raccoon video?
Yes.
Yes.
All right, I got one here, but I have to scroll through some pictures, so no peeking.
The only reason why I came to class today was to see this video.
Because I can't, it won't let me do that.
No other motive.
Hold on.
Yes, bro.
Wait, I know what I'm gonna do. I'm gonna hide my video for a second. Stop video. Zoom with B Britain. Okay, so hold on. I'll find the raccoon video and then I'll show it to you. That way you guys don't have to see all the terrible things that I do. All right. I think I've got this here. Can you see the spaghetti?
Is that spaghetti?
Yeah. Yep.
Look at that.
Oh.
I can already hear you. What you snacking on, huh? What you eating? Want to try some spaghetti? Oh. He lives in the drain near my house. Nope, you can't take the whole thing. Yeah, you can eat that. Ooh, spaghetti's fun. Guys, this is what I do when I'm not teaching class. I'm sorry, this is my life.
Feeding the raccoons.
Yep. Yeah, pretty much. Some mushrooms and some bacon.
Well, it's pretty funny that anybody who's watching this later will get to see this video now too, because
yeah, exactly. It'll be preserved for all time.
Put on the YouTube channel.
I know all my friends love my Instagram now. They're like, Brendan, we didn't really care about your Instagram, but now all we want to do is see videos of the raccoons. So please.
You have an Instagram?
Yeah, follow me. Follow my raccoon videos. I try to post one.
I already do.
Look at this guy. Look at him go.
Hey, how about that, huh?
They're actually kind of dangerous, right? Because a lot of them carry rabies. Oh, Morgan, I love your dog. That's great.
Red tomato. That's pretty yummy. All right, come on, take the rest of this.
A lot of these raccoons actually carry rabies, and some of them, they're not even rabid themselves. They're kind of tolerant to rabies. So it's pretty scary because when I'm feeding them, I usually put on a big, thick rubber glove because I don't want them, if they scratch you or if they bite you, they can give you rabies and then your life is over. You immediately have to go to the hospital. You have to get 2 shots. You have to go back 3 or 4 more times for shots at different time periods.
That's like 10.
Wait, so what happens when you get rabies? Is that just like
You die.
You just like die?
You become hydrophobic. Yeah, your brain swells. You go through hallucinations and you get violent and then you die. It's really fucking horrible.
I'd rather just live with the rabies than go to the hospital.
No, rabies is like a 100% fatality rate. You can't live with rabies. You die with rabies.
You die immediately once you get it.
Anyways.
I have a pretty impressive immune system.
Well, then you come over here and feed the raccoon. We'll put the banana chips in your hand.
It's not the first time I've played with a raccoon. I can do it.
Okay. Hey, guys, I know we went on a bit today, but I had a blast hanging out with you. The lecture, I didn't get as far as I wanted to, and, you know, that's just the way the cookie crumbled today. The homework was good, but it took a while. Thanks for putting up with me. You guys are going to submit this, right? Do you know what to do?
Yeah.
All my stuff's in Blackboard already. I just have to submit it.
Yeah, one more time for those of you and also watching at home who might not know what to do or watching later on at home. When you go to, can you guys see my screen?
Yeah.
Yeah.
You go to the home, Tim, you can be exempt from this. You can send me by email because you don't have access to this yet. But those of you who do, I think it's probably easier to submit through Blackboard. And let me just show you. If you go to the homework section, we just did homework 6, chapter 14. And when you click on it, there's a place to attach files. You can either just take a picture with your cell phone or upload the file with a scan, and then you browse your computer and upload it there, and I'll be able to grade it in the grading center, okay?
So I'll let you know now. I typed the actual work itself, so you have a typed version, and then you have 2 pictures of the notes that you usually have us take as we're doing this.
All right, but remember, guys, if you are using if you're using a Word editor or a text editor to submit these files, you need to do all your math using an equation editor, right? Did we talk about this last time?
I did all the equations on the paper.
By hand?
Yeah.
If you're using a Microsoft Word to type this up, I better see all the math done all nice and neatly in an equation editor like this, right? I don't want to see I want to see your scientific notation looking nice and neat like this. 6 where are we here? 6 times, and then you got to go to your scripts here. This is what the mass of the Earth needs to look like if you're typing it up. I don't want to see no carets and asterisks and stuff. You see what I mean?
Okay,
Wait,
yeah, I can fix that.
Can I just take a picture of the paper I wrote with the hard work and blood and
that's
sweat?
the easiest way to do it. Just snap a photo of the picture that you worked on and
that's what I'm
upload
doing.
that. You can upload a JPEG, okay?
All right, sounds good.
Okay, so
Where do I upload this, Professor?
Blackboard, right?
Are you still seeing my screen?
Yeah.
So go to the class, go to homework.
Okay, good news is I still have that fixed, so I can edit this.
Click on chapter 14, Sal. And then under chapter 14, it says 25 points possible, and you make your assignment submission, browse computer. Is that making sense to you?
Yeah.
Now, that's probably better than emailing because I'll get your homework emails jumbled up with all the other emails I get, and it'll be confusing. Tim, until such time as they will allow you to join the class, I'm going to let you email me if that's good with
I don't
you.
even know if they're going to let me do, like, if it's even possible to do it.
Exactly. I started thinking about that, and it might just be too big of a pain in the ass. So as long as I'm only getting 1 or 2 submissions by email, I'll remember, okay, I got to make sure I get Tim's. The chaos is going to happen if I have to get 40 submissions that way. It'll be a bit messy. So hopefully you guys can just figure this out. If not, talk to me. I'll walk you through it again. Okay? All right.
Good. See ya.
So everyone cool? Do we have any other questions or concerns? Or
We're good.
I'm good.
Should be good.
I'm good.
all right, we're going to get through this, guys. Next week I should have a better camera. We're going to finish the sun. We'll move on to stars. Once again, we'll do our lab on Tuesday, and we'll do the homework on Thursday. Okay?
Okay.
Not all of them will be this long, so we'll make it better. Okay. Until next time, sayonara. Okay?
Sayonara.
Yeah, see you later.
I'm going to save that chat too. Save the chat. And I'm going to stop recording.